Okay, so today we're going to find limits of functions using properties of limits. So there's a whole bunch of properties here that I would like you to look at, and what I want you to do is maybe pause the video and look at all these properties, and then we'll do some examples. Let me scroll so you can see them. So you can pause it at any time, read them please. Okay, so now that you finish reading all those properties of limits, let's evaluate some limits. This time we're not going to use a table, and we're not going to use a graph, at least not yet. But according to the theorem from the previous page, if I look at this 7, that's a constant. And according to that first property or theorem that you saw, it said that the limit of f of x as x approaches a certain value, if that f of x is a constant, then the limit is just a constant. So for this one, the limit as x approaches 5 of 7, it's just 7. The reason is because 7 is a constant, and according to the property, the limit of a constant is always going to be the constant. Now let's look at the next one. So this one, we want to find the limit as x approaches -2 of this function here. Now, to make things easy, when you want to evaluate a limit, you just use direct substitution and see what you get. So let's use direct substitution. What that means is this: you're going to get rid of the limit, and you're going to plug in that -2 wherever you see an x. So let's do that. So it'll be, let's see, 3. The x becomes -2 plus 1. Now we're just going to simplify. First inside the parentheses. So we have 3. Inside the parentheses, -2 plus 1 is -1. And that we just multiply 3 times -1, which is -3. There. We found the limit as x approaches -2 of that function there. Okay, let's go on to number 3. We're going to do the exact same thing. All you have to do is plug it in, use direct substitution. So we're going to get this 8, and we're going to plug it in there. And also get rid of the limit sign. We don't need it anymore once we evaluate. So it'll be 1/4 cube root of 8. So now first we evaluate the cube root of 8. So it's 1/4. Cube root of 8 is 2. So now in reality we have 1/4 times 2. Well, 1/4 times 2 is 2/4, which becomes 1/2. And that is the limit. Okay, number 4. Notice that this time we have a different variable, t, and a t, but that doesn't really matter. That's just a dummy variable. That's really what it's called. But we're going to evaluate the limit the same way. So let's go ahead and plug in the 2. So again, t is approaching 2. So this t is approaching 2. So let's get rid of the limit and then plug in the 2. There. Let's plug it in. So it's going to be square root 3 times 2 plus 4. 3 times 2 is 6 plus 4 is 10. So square root of 10. Square root of 10 cannot be reduced anymore, or simplified, I mean. So that is our answer. Let's move on to one that looks a little bit more complicated. So again, this one is the limit as x approaches 2 of this function. So let's use direct substitution and replace all the x's with the 2. So here we go. And remember, you don't need the limit sign anymore. So it'll be 2, parentheses, square root of 2 times 2 plus 4, all of that raised to the 1/3 power. So now let's simplify. In here, inside the radical, we have 2 times 2, which is 4. So I'm going to write 2 square root of 4 plus 4 raised to the 1/3 power. So let's see, we're in pre-calc. So square root of 4 is 2. Again, square root of 4 is 2. There's a 2 outside. So square root of 4 is 2 times 2 is 4 plus 4 is 8. So now I have 8 raised to the 1/3 power. And the 1/3 power means that I need to take the cube root of that number. So basically what I'm looking for here is the cube root of 8. The cube root of 8 is 2. And that is our limit. Okay, next example. Another limit. Let's use direct substitution again. So this time we want the limit as x approaches 3 of this function. So like I said before, just let's use direct substitution. Let's plug it in. So it'll be 3 squared plus 5 over square root of 3 times 3. Let's start simplifying. 3 squared is 9. 9 plus 5. 3 times 3 is 9, so square root of 9. 9 plus 5 is 14. Square root of 9 is 3. And 14 over 3 cannot be simplified anymore, so we leave it like that. That is our answer. Okay, so now we're going to do another one. We're going to do the same thing. So now, let's see. Let's read it again. Limit as x approaches -2 of this function. So let's replace all the x's with -2. So -2 plus 2 over -2 squared minus 4. Make sure you put parentheses around the -2 when you square it. So in the numerator, we're going to get 0. And in the denominator, we're going to get 0. So now we're getting 0 over 0. So that tells me that that's a problem. So let me rewrite them. Oops. Let's see. Let me move this out of the way. Okay. So here we go. Anytime when you plug in, use direct substitution, and your numerator is 0 and denominator is 0, that's called an indeterminate form. And what that means is that we have to somehow manipulate the function so we'll get a limit. So now, I noticed that x squared minus 4 is a difference of 2 squares, and we can actually factor it. So let's factor that. Now, we need to keep the limit sign. So limit as x approaches -2. The numerator is going to stay the same. Nothing changes. X plus 2. The denominator, we're going to factor it. It's going to be x plus 2, x minus 2. So now, I notice that the x plus 2 cancels this x plus 2. So now, let's rewrite it. We still keep the limit because we haven't evaluated. So limit as x approaches -2. Now, don't make this mistake, please. In the numerator, even though we canceled it out, something is still in the numerator, a 1. And in the denominator, we have x minus 2. So now, what we're going to do is we're going to evaluate this limit. So limit as x approaches -2 of this function. Let's replace the x with -2. Now, when you evaluate the limit and you're using direct substitution, that means that the limit sign, you no longer need the limit sign. So 1 over, the x becomes -2 minus 2. And then -2 and -2 is -4. So this is 1 over -4. And I mean, you can leave a negative in the denominator or just put it in the middle. So -1/4. Okay, let's move on to another example that is similar to this. Now, let's see. So this one, we are looking for the limit as x approaches 3 of this function. So first, let's use direct substitution. But before that, look, if this x becomes as 3, so we have square root of 3 minus square root of 3, that's going to give me a 0 in the numerator. And if I plug in a 3 here, 3 minus 3, that's also going to give me a 0 in the denominator. So that tells me that I need to manipulate it somehow. Now in this situation, I don't see a difference of two squares. What I do see is square roots. So what I'm going to do is I'm going to keep the limit sign. And this is another way of manipulating a 0 over 0 indeterminate form. What you want to do is, if you have radicals, you want to multiply the numerator and denominator by the conjugate. And usually the conjugate is going to be the one with the square roots. So the conjugate of this numerator, it's going to be the exact same thing, except we're going to change the minus to a plus. So let me show you. So we're going to multiply top and bottom by the conjugate. There we go. Now, the good thing about multiplying conjugates is that it's very easy. Let me show you an example of a conjugate that you know very well. So if I have a plus b and I multiply it with a minus b, they're conjugates. This is a special property that we've done before. So this gives me a squared minus b squared. So that's why I'm multiplying by the conjugate. So what that tells me over here, if this is a and this is b, this is a and this is b, then that means, according to what I just showed you, we're going to get this. So limit as x approaches 3 of square root of x squared minus square root of 3 squared over, now the denominator we're not going to distribute, we're just going to leave it exactly the same. So it'll be x minus 3 times square root of x plus square root of 3. Now let's simplify. When I square a square root, they cancel out. So now I have limit as x approaches 3. Square root of x squared is just x minus square root of 3 squared is just 3. Now notice why I didn't distribute the denominator, because now I'm able to cancel something just like we did in the previous problem. So I noticed that x minus 3's, they cancel out. So let's rewrite it. Ran out of space. Let's see. Limit as x approaches 3. Numerator, we're left with a 1. Denominator, we're left with square root of x plus square root of 3. Now we will evaluate. Now remember, to evaluate, I do not need the limit sign anymore. So we have 1. Oops, sorry. So I have 1 over square root of 3 plus the square root of 3. And my final answer is going to be 1 over 2 square root of 3. Okay, now for these, it says find each one-sided limit using properties of limit. So it's basically telling me find the one-sided limit. But we do not have a graph, but that's okay because we have a function. So even though it's asking us to find the one-sided limit, all you have to really do is plug it in. Just plug it in. That's all you have to do, direct substitution. So then this will be 3 squared minus 4. 3 squared is 9, minus 4 is 5. It's that easy. Let's do the next one. Same thing. This time we're approaching 2 from the right. But in this situation, just plug it in again. So we have 2 square root of 2 squared minus 4 plus, that's going to be outside. So let me erase a little bit here. 3 times 2. Let's simplify. So this is 2 square root of 0, because 2 squared is 4, minus 4, plus 6. But the square root of 0 is 0 times 2 is 0, so therefore answer is 6. Okay, now let's look at a different type of limit. Now for this one, it says use the information below to find each limit. But notice that this time, they didn't give me an actual function. What they did give me was the limit. So the limit as x approaches c, and c could be anything. So limit as x approaches c of f of x is 5. Now I also know that the limit as x approaches c of g of x is 2. And the limit as x approaches c of h of x is 0. So we actually have the limit. We don't have the function, but we have the limit. Now this c could be anything. So it's the same. So now, let's see. According to one of our properties, when we have a constant and it's being multiplied with a function, you can literally get the constant and move it to the front. So let's do that first. So that 5 is going to go outside. 5 limit as x approaches c of f of x. Now, what I want you to notice is this. This part right here is this. Again, let's look at it. This right here is this. So we know the limit. It's equal to 5. So now we have 5, that's the outside 5, times 5, the limit. So that will give me 25. Easy. Let's go on to the next one. This time we have three functions, but it's okay. Notice that we want to find the limit as x approaches c of f of x divided by g of x minus h of x. Easy again. So now we don't need the limit sign anymore because we're going to evaluate. Now we want the limit of f of x. The limit of f of x is 5. So that's going to be 5 over the limit as x approaches c of g of x is, where's my g of x? 2. So that's going to be 2 minus the limit of h of x. That will be 0. So 0. So that's just going to give me 5 over 2. Alright. Now, there's another property that said that if you are multiplying two functions, then you can just multiply their limits. And this 4, this time you cannot take it out because it only belongs to the f of x. Actually, you can't take it out because these are multiplying, so that's okay. If it wasn't multiplying, then you couldn't take out the 4. But since it's multiplying, yes, you can take out the 4. So let me rewrite it. So it'll be 4 limit as x approaches c of f of x times g of x. So now, if you recall, let's see, 4 parentheses, the limit as x approaches c of f of x was 5 times the limit as x approaches c of g of x, I believe it was 2. Let me double check. Yes, it's 2. So that's going to be 2 there. So now we do the math. 4 times 10, which gives me 40. Easy. Let's try one more like this. Now, if you read the rules, like I asked you to, those properties on the first page, whenever you have a limit and you have a radical, then you can just move the limit inside. So limit as x approaches c, 5 times g of x minus 3. So now, let's see, we have cube root of 5 times, what was g of x? G of x I believe was 2. Let me double check. Yes, 2. And then minus 3. So 5 times 2 is 10. Minus 3 is 7. So we have the cube root of 7. And since we can't simplify that, that's our limit. Okay, so now we're going to look at a combination of what we learned using a graph and adding functions, dividing functions, subtracting functions, so the same thing. So let's start looking at it. It says use the graphs of the functions and properties of limits to find each limit if it exists. So let's start with 15a. Says to find the limit as x approaches 3 of f of x plus h of x. So let's find the limit as x approaches 3 of f first. Now here we have three graphs. F is the blue graph, G is the pink, red, and H is the black. So again, it's asking us to find the limit as x approaches f of x plus g of x. So let's find f first. So limit as x approaches 3. So remember, when we first did this, we have to look at both sides. So we're approaching 3 from both sides. Notice that the y value is 0. So that limit is going to be 0. We don't need the limit sign anymore. Plus, now we need to look at the limit as x approaches 3 of h of x. So let's approach 3. But let's look at h of x. What y value are we approaching as we approach 3? That y value is negative 2. So it'll be 0 plus a negative 2, which is just negative 2. Okay, for the next one, notice that it's exactly the same thing, except we have a 2 there. So that means just multiply your answer by 2. Now we already have the answer. It's negative 2. So in reality, all we have to do is say 2 times negative 2, which is negative 4. Done. Now we already know the values for f of x and h of x as x approaches 3. So if you look at this one, C, we have the limit as x approaches 3 of f of x over h of x, but we already know what the limit is for f of x. It was 0, and the limit as x approaches 3 of h of x was negative 2. So 0 divided by negative 2 is just 0. Okay, let's look at the next one. The next one, we are approaching 3 from the left. Again, 3 from the left. See the little minus sign? That means from the left. And we're going to look at g of x and h of x. So let's go to the graph. So we're looking at the red graph and the black graph. So we're approaching 3 from the left. We are approaching 3 from the left. Again, 3 from the left. That means that y value is my graph approaching as I approach 3. It looks like 6. So again, if I approach 3 from the left, my graph is approaching 6. So we know it's 6. Now, as we approach 3 from the left, let's follow our h of x. Notice what it's doing. It is approaching negative 2. Again, it is approaching negative 2. It doesn't mean that it's equal. It's just approaching. So we said 6 and negative 2. So let's go back. We're going to add them because that's what it says to add. So again, the value as or the limit as x approaches 3 from the left of g of x was, we said 6, plus the limit of h of x was negative 2. So 6 plus a negative 2, that gives me 4. Easy. Okay. Now, last one. We already have the values. So we said that the limit as x approached 3 of f of x, I believe, was 0. And of h of x, we just did, it was negative 2. So all we have to do is plug it in. So f of x was 0 minus 2 times h of x was negative 2. But then I have this exponent out here, 3/2 equals, let's simplify inside. So 0 minus 2 times a negative 2 is 4 positive 3/2. Now the 3/2 power, that means that I'm going to take the square root of 4 and then raise it to the third power. Again, the 2 in the denominator tells me take the square root of 4 and then raise it to the third power. So the square root of 4 is 2, and I'm going to raise it to the third power. 2 to the third power is 8. That is our limit. Okay, last two examples. This time we have a piecewise function, and it wants us to do this. For the following problems, find the limit as x approaches c from the left of f of x and limit as x approaches c from the right of f of x for the given number c. Based on the results, determine whether the limit as x approaches c of f of x exists. So what they want us to do is find the left-hand limit, the right-hand limit, and see if they're equal to each other. If they're equal to each other, that means that the limit exists at that c value. If they're not equal to each other, then the limit does not exist. So let's get started. For number 16, our c is 1. So that means we want to approach 1. So we're going to start off by saying limit as x approaches 1 from the left of f of x equals. So now we have three choices. This f of x is made up of 1, 2, 3 functions. Now from the left, this is what it means. Think of the number line, and let's go to 1 there. If I approach 1 from the left, that means I'm coming from the left, moving towards the right. But what I have to do is consider all these numbers that are to the left of 1. That means that all these numbers are going to be less than 1. So that means I need to pick the one that has x less than 1. So 3x minus 1 is the function we're going to use. So again, here we go. Limit as x approaches 1 from the left. Our function is 3x minus 1. 3x minus 1. And now we do what we've been doing. Just plug it in. So it'll be 3 times 1 minus 1. 3 times 1 is 3 minus 1 is 2. So we found the left-hand limit. Left-hand limit. We don't need that, but it's okay. Now we want to find limit as x approaches 1 from the right of f of x. Now, if we go back to this and we're approaching from the right, you have to consider all these values to the right of 1. That means that they're all bigger than 1, greater than 1. So this is the function that we want, the one that is greater than 1. So it's 2x. So now we come here, we rewrite it. Limit as x approaches 1 from the right. Our function was 2x. Let me double check. Yes. So now we do direct substitution. That means plug it in. So it's 2 times 1, which is 2. Now the right-hand limit is also 2. They're equal to each other. So now that tells me that the limit as x approaches 1, because now we want just the c by itself, of f of x is equal to 2. The reason is because the left-hand limit and the right-hand limit are equal to each other. So therefore the limit at 1 is 2. Okay, last one. Let me just move this up a little bit. Okay, this time the target, our c, is 2. So we want to find limit as x approaches 2 from the left of f of x. We're approaching 2. So again, let's think of the number line. Number line at 2. Oops. And from the left means we are approaching from the left, so this way. From the left means that all these values to the left of 2 are less than 2. So that means I have to use this function, 5x plus 2. So let's write it again. Limit as x approaches 2 from the left is 5x plus 2. Yeah. So now we use direct substitution. Plug it in. So it's 5 times 2 plus 2. And 5 times 2 plus 2 is 12. Okay, now let's do from the right. So limit as x approaches 2 from the right of f of x. Again, if I go back to my little number line that I made here, from the right, means that all these x values are greater than 2. Again, these are greater than 2, so that means this function. That means this function, 1 plus 3x. So we're going to go back. We're going to replace f of x, so limit as x approaches 2 from the right, of 1 plus 3x. Next step, use direct substitution. So 1 plus 3 times 2. If I simplify that, 1 plus 3 times 2. 3 times 2 is 6, plus 1 is 7, so 7. So notice now that the one-sided limits are not equal to each other. When we approach 2 from the left, we get 12. When we approach 2 from the right, we get 7. So what that says is that the limit as x approaches 2 of f of x does not exist because the one-sided limits are different. Okay? So again, in order for the limit to exist, the one-sided limits have to be equal to each other, just like on this problem.